Okay, so good morning, quantum enthusiasts. I'm really happy about today's lecture because it's one of my favorites. We're going to see like this quantum bias busting algorithm. We're going to see like an actual algorithm for solving a problem with a quantum computer, arguably a problem you might even care about, which is great, unlike the mystery toggles. And indeed, some people would say that this quantum bias busting algorithm is maybe our best evidence, our best formal evidence that quantum computers can do stuff that classical computers cannot. So that's what they're supposed to be able to do, right? I mean, they're supposed to be able to do stuff that classical computers can't. So far, we haven't really seen it. Well, maybe we've seen it. Like I showed you that mystery toggles thing on lecture 1. Where it was true that quantum could do something like really amazing, like solve the mystery toggles in one application, whereas classical code would need, n. But that was kind of for a bogus problem, right? I mean, like at the beginning of that problem, I was like, imagine there's like a mystery piece of code that like contains all these if-then toggles, and you're not sure which ones, and like you can't look into it, but you can call it. Like that's a pretty weird setup, right? I mean, that's not like really a legit problem. It's like designed for illustrative purposes. We're going to analyze exactly that next lecture, by the way. But this bias busting thing, it's like for a legit problem, and quantum computers can do something that classical computers basically cannot, assuming something like p does not equal np. The only downside is this thing that they can do is totally useless. It's totally practically useless. So again, like it's not so awesome. But at least it hopefully, convinced people back in 1992 or whatever that, hey, there's something potentially here, that quantum has a real advantage over classical. Okay, so last time, we spent like a long time justifying this fact that like anytime you have a Boolean function and you can write regular old classical computer code to compute this Boolean function efficiently, then you convert that code into quantum code that also computes the function in a sense, but on qubits rather than on bits. And why do we work so hard to achieve this? We work so hard to achieve this because we wanted to like plug it in to this quantum computing algorithms paradigm, if you will, from lecture 6, this glorious paradigm that will apply to like 2 problems. But it's the best we got. And let me remind you of how this Hadamard transform, Fourier transform paradigm went. I'll just, in fact, remind you of the first couple of steps. So the first step of this paradigm was this, like use your quantum computer to put n qubits into the so-called uniform superposition, which means the state where you have like amplitude 1 on every single one of the 2 to the n basic states. Okay, that's an unnormalized state, but it's more nice to work with unnormalized states here. And we'll see later today that's like quite easy to do with quantum code. And then step 2 of the paradigm is like now finally deploy your quantum code that can compute the function f you care about on qubits. And then by definition, like when you do that, the state's amplitudes will then encode all 2 to the n possible input-output pairs of the function f. And this is truly amazing. Like by doing like a regular number of, like a reasonable number of operations in the real world, you've got this object, n electrons, maybe 1,000 electrons, whose physical state encodes like 2 to the 1,000, all the 2 to the 1,000 entries in the truth table of f. That's truly amazing. Now, where you go from there is maybe we don't know so easily, but let's start this lecture today by like getting up to here and being proud of ourselves for that, because it seems pretty great. Okay, so the first step of this paradigm will be to prepare the uniform superposition. And I'm here to tell you that this step is real easy. And even though it produces 2 to the n amplitudes, well, these like amplitude trees get real wide real quick. It's not that hard. You can do this with n instructions. So here's the claim. This code, or this refers to what I'm going to write, prepares the uniform superposition on n qubits. And, well, step 0 is you just make the qubits, a new qubit B1 through Bn. Okay, now you got n qubits. And always think of your mind, n is like 1,000 or something, some reasonable number of bits for your input. And now, step 1, it's really Hadamarding, but we'll call it add and diff. Add and diff B1. It's really just Hadamard all to add and diff B2. And then, down to line n is like add and diff bn. Okay, so that's n instructions. If n is 1,000, that's like n tasks that you have to do. But, hopefully you can just take each of your photons or whatever and do some little operation on each of them, and you've accomplished this quantum code. Okay, so I claim that this code indeed prepares the uniform superposition. And we'll just do like a proof by example, and you will agree with me, I hope, at the end. So let's do a proof by example. And we'll do it in the case that n is 3, because that's easy to draw. Okay, so now I have to draw this like crazy picture again, because I want to depict a state of 3 qubits, which has like 8 amplitudes. So bear with me as I try to draw this. Got this, this. Wait, what happened? I got trapped here. This? Whoa, no, that's terrible. Hold on. This is bad. What happened here? Okay, good, thank you. Oh, this one needs to be at the back. Okay, got it. Okay, cool. Did I do it? Yeah. Okay, so like each of the n qubits corresponds to a direction, and how you do this is not important, but like, I don't know, I chose this way, B3. Okay, and then like, this is like 0, 0, 0. All right, let me just do this, 100. I should have pre-drawn this, but oh well. Okay, I didn't put the angle brackets, but you can deal. Okay, so great. So this is going to like store our 8 amplitudes. So after line 1, we know that the state of the qubit is like all the amplitude is on 0, 0, 0. N is 3 here. So we have like all 1 of the amplitude on 0, 0, 0. And 0 amplitude everywhere else. But I'm not going to write zeros. I'll just let it be blank. It should be this. Yeah. Okay, thank you. Yeah. Okay, cool. So, all right, let's remember how it works. So, like, line 1, add and diff B1. So, like, the B2 and B3 stuff doesn't change. The B1 stuff you do have, you have to pay attention to. So the B1 direction is, like, up and down. So basically, we've seen this several times before. Like, you're basically going to do this, like, add and diff operation on all the up and down edges. And the add will go into the 0 slot, which is on top. And the diff will go into the bottom slot, which is on the bottom. So like, almost everything is like 0 amplitude. I didn't write a red 0, but it's almost all zeros. Here on this vertical edge, we have 1 here and 0 here. So 1 plus 0 is 1, and 1 minus 0 is 1. So after line 1, we have like 1, 1. Okay. Okay, now we're going to do add and diff on B2. So it's like doing the same operation in like the B2 direction. So basically now we're like pairing up all the vertices in the horizontal direction. We have these like 4 horizontal edges. And same deal, like the sum of the 2 amplitudes goes on the 0 side, which is the left side, and the difference of the amplitudes goes on the 1 side, which is the right side. So on the back face, everything is 0, so nothing is happening. On the front face, okay, we have this horizontal edge, 1 and 0, so 1 plus 0 is 1, and 1 minus 0 is 1, so we get to here. And like here, we're also going to get to, this is 1 plus 0, this is 1 minus 0. Okay? So after this instruction, you kind of see we sort of have the uniform superposition on the front face. We have like all 1s on the front face. And basically, like the next line with B3 is going to like effectively copy all those 1s also to the back face. Right? So the next line is add and diff in B3. That's in the like in-out direction. So for like every in-out edge, you have to like put the sum on the 0 side and the difference on the 1 side. Okay, and it's always going to be like 1 plus 0 is 1, so that goes here. And 1 minus 0 is also 1, so we get 1s all on the back face. Okay, and so, ta-da, we did it. If n was 3, we got amplitude 1 everywhere. Okay, and if like you're still like, oh, I'm not totally convinced, like if n was 4, okay, it'd be like we have like another, like this is my best way of depicting, if you have 4 qubits and like this is like the B4 direction is going from this cube to this cube. And so really, like, all of these would have zeros on them. And, like, these would all be the same, except they'd have 1s at the end. And all the first 3 instructions would just still have left all the amplitudes here 0. But then if we did, like, add and diff on B4, it'd be like all the sums go on this side, all the differences go on this side. So all these 1s would stay 1s, and then the differences are all 1s. So they'd, like, get copied over here as well. Okay, and then I really cannot depict 5 qubits, but I hope you're now satisfied. Okay, so great. So that's it. So in some sense, this is done. And with like a reasonable number of instructions, basically n instructions, we've got this cool state where like we have amplitude 1 on every single possible 2 to the n bits or n-bit string. Okay, so then let's think about like what happens if we do this. Like, let's say we have like some code for. Let me just skip toggle and we'll focus on minus. So let's say we have some code that computes a like regular classical code that computes some Boolean function f with 1 output bit. So imagine we have like some function f mapping n bits to 1 bit. And somehow we want to like know something about this function. We have classical code that computes it. So we can convert it using last lecture to quantum code that does if then f then minus. And if f's classical code had a reasonable number of instructions, so too will the quantum code that computes if f then minus. And now we can do it. Now we can apply f to this state. Well, we can apply this line to this state. And I mean, let's remember what that does. You know, we're in some complicated state here now that looks like, you know, amplitude 1, 1, 1, 1, 1, 1, 1, 1 on like every possible n-bit string. And now, if f then minus is like a pretty simple instruction that just takes like the basic state you're in and like maps it to the same basic state, except maybe with like a minus sign, like maybe with amplitude 1 or minus 1. And whether or not the amplitude is 1 or minus 1 depends on what f applied to this string is. So the upshot is like after line 2, we get to this pretty glorious state. It looks like this. We have amplitude plus 1 on all the basic states, b1, b2, up to bn. This stands for like an n-bit string, where the function value is 0, and amplitude, this is small a, minus 1 on all basic states with the function value being 1. Okay, so this is a pretty complicated state insofar as, you know, it has a non-zero amplitude on every possible basic state, and all these amplitudes are plus or minus 1, and like the pattern of plus and minus 1s is really like comes from the truth table of f. Okay, so I would say that like the entire truth table of f, I'll do a little example in a second, table of f in plus or minus 1 notation. Okay, this is a phrase I'm going to start using. I'll explain it in a second. Is like loaded into the state of our n qubits. Okay, I'm going to in fact start like saying like this phrase to like explain what happened after line 1 and line 2. Like we managed to load the entire truth table of f into the state, into the amplitudes. And this phrase plus or minus 1 notation just refers to the fact that like, okay, normally when you write the truth table of f, you're like, okay, the values of f are 0s and 1s. But by the phrase in plus or minus 1 notation, I mean this little mapping where you change 0 to plus 1 and 1 to minus 1. Which we do because that was like the natural way to like quantize f's operation. Okay, so let me just kind of give you a little example in case it wasn't totally clear. I want to do it in a nicer color. Okay, so my favorite little function to use as an example is on 3 bits. It has 1 output bit. And it's the majority function. I think this was on the last quiz. It's a function that takes in 3 bits and outputs like the majority of the bits. So I can just draw its truth table, like in the normal way you draw a truth table. Okay, so those are all the 2 to the n possible input strings. It doesn't look too impressive what I'm going to do here because n is 3, because I can only write so much. But like, you have to remember like the impressive fact that like it's perfectly normal to compute the majority of like 1,000 bits on your computer. But like, you cannot write down 2 to the 1,000 rows. That would not fit inside our universe. Okay, so the majority of these bits, okay, it's 0, 0, 0, 1, 0, 0, 0. Whoa. Wait, 0, 1, 1, 1. So that's the normal truth table of this little Boolean function. And then let me use this phrase, like in plus or minus 1 notation. It just means converts the zeros to plus 1s and the 1s to minus 1s. Okay? And what this means was, like, if we were to now literally do this operation where f is the quantum code that implements if majority of 3 then minus, then the new state would like exactly encode the truth table of this majority function. So let me draw it here. Ignore this now. So like the majority of 0, 0, 0 is 0, and like the plus or minus 1 notation for 0 is plus 1. I don't know, the majority of 1, 0, 1 is 1, and the plus or minus notation of that is minus 1. So it'd be minus 1, so plus 1, minus 1, plus 1, minus 1, minus 1, plus 1. Okay, so that would be like the new state after doing this line. And again, it like doesn't seem so impressive when n is 3, but like it really is impressive because like when n is n like 1,000, like you got all 2 to the 1,000 possibilities here and like the proper plus or minus 1 value. I forgot to do the prize pantry, so here we go. Can pass these around. Oh, it's okay. Okay, so any questions about this? Great. So it seems like at this point, it really seems like quantum computing has done something truly amazing for us. We're like, oh my god, we like computed all possible values of f simultaneously with like one call to f, basically. But now the question is like, now what do we do? Like, what do we do with this? And probably your first instinct to what to do, okay, maybe it isn't your first instinct because it's a very bad thing to do. But a thing you might think is like, maybe now is a good time to like extract all. Like, let's measure. But that would be a very bad idea. Like, what will happen if you do extract all now? Yeah?
You just see a random outcome, like a uniform outcome.
Yeah, you'll just see like a truly random n-bit string. Because what do we know like about extract all? The first thing you should do is like get back to a normalized state. We're not in a normalized state here because like the sum of the squares of the amplitudes is 2 to the n. So you'd have to divide by the square root of 2 to the n. But like if you don't worry about this normalization for a second, the other thing you have to do once you do that is to square all the amplitudes, and those give you the probabilities. You see, if you square these amplitudes, like you're just going to get like all plus 1s. Like everything is going to have plus 1 because negative 1 squared is plus 1. So they're all the same. So when you put in the normalization, you still have the property that like all the probabilities are the same. So if you did extract all now, it would literally output each of the 2 to the n possible strings with equal probability, which is totally useless, right? Like I can do that. Like I can write a code that says like for I equals 1 to n, print a random bit. That's nothing. So if we do extract all now, we kind of wasted it. We screwed up. Like we didn't get any advantage out of this situation. So as I maybe mentioned back in lecture 6, somehow, and this is a bit vague, but like somehow what we need to do is use the glorious power of like interference or cancellation. Like we somehow need to be like, oh, cool, like some of these are positive and some of these are minus. So if we do some operations like, Hadamard or whatever that mixes them together, some things can cancel out to 0 and some things can like not cancel out to 0. And maybe, like just maybe, we can do something where like we get all sorts of cancellation, and like we get 0 amplitude on all uninteresting things, and we get like all the amplitude on like the one string that reveals some secret about f. That sounds weird, although that is what happens in mystery toggles, right? Like we get into some funny state, and we did some things, and then somehow like almost all the amplitudes cancel, and you're left with like all the amplitude on like the one string which reveals what was inside mystery toggles. So that's what maybe you could hope to happen.